let's take a matrix. I'll call it A. Let's make it a 2x3 matrix. 1, -4, 3, -2, 5, 7. How have we thought about such matrices so far? We have thought of them as defining linear transformations, and we've thought about finding kernels of the transformations, which is the same as the null space of the matrix, image of the transformation, which is the same as the column space of the matrix. This defines a transformation, T of x equals A times x. Since this matrix is 2x3, you have to multiply A by a 3-dimensional vector. The domain is 3-dimensional space. But as a linear combination of these columns being 2-dimensional vectors, the codomain is going to be 2-dimensional space. Notice these 3 vectors, these 3 column vectors, if I drew them as arrows in the plane, I made them somewhat random. They're not going to be parallel to each other. 1, -2 is going to be a vector about like this. -4, 5 is going to be a vector about like that. 3, 7 is going to be about like that. They're not parallel to each other. It should make intuitive sense that because of that, if you form linear combinations of these things, you will get every vector in the plane. These 3 vectors, I'm going to give them names, say v1, v2, and v3. This collection of vectors spans the plane, R2. What do I mean by that? I mean, I can get any vector in the plane by a linear combination of these vectors. An equivalent way to write that is this notation. The span, and usually use a capital S, span of v1, v2, v3 is the entire plane. That's equivalent to the linear transformation being onto. This is equivalent, these things, is all equivalent to T is onto, which is also equivalent to the column space of A and the image of T, which are the same thing, being all of R2. These are all equivalent to each other. How do you prove this? I haven't really proven it. I just said it's intuitive. You prove it with row operations. If you go to reduced row echelon form here, you're going to get a pivot in every row. You're not going to get a row of zeros, is essentially the reason. Let's go ahead and do it with calculator. Well, okay, let's do it with Mathematica. Since I already had Mathematica up. And I'll show you how to do it if you haven't done it before. And we want the answer to look like a matrix. Row reduce is what you use. 2 capital R's. I don't know if I've mentioned this. To add a column in Mathematica, you do a control column, a control comma. Comma starts with C, just like column starts with C. To add a row, you do a control return. Return starts with R, just like row starts with R. But I want a 2x3 matrix here. 1, -4, 3, -2, 5, 7. There's the RREF for this. I've got a pivot in each row. No row of zeros. That's enough to prove that the transformation is onto. Why? Well, if you imagine doing an augmented matrix with an arbitrary A and B over here, a 2x4 augmented matrix, and did the row operations, I'd have some transformed version of A and B over here, and I'd be able to solve. Because I have a pivot in every row, I'd be able to solve. There is a free variable. X3 is a free variable. I could solve for X1 and X2 in terms of X3 and whatever the constants were. However, they got transformed under the RREF operations. I'd be able to solve any system of equations. They'd all be consistent. Okay. Geometrically, The equations defined by this matrix would define two planes in three-dimensional space. Effectively, they'd intersect along a line. The solution set would be one-dimensional. The kernel would be a one-dimensional line through the origin. There's one free variable. And yeah, let's relate these things now to that idea as well. Going from three-dimensional space to two-dimensional space, a lower dimensional space, it should be intuitive that there's some sort of collapsing going on. And that includes more than just the zero vector getting mapped to the zero vector, the kernel being non-trivial. And in fact, what would the kernel be? The kernel here of this transformation, because I have the RREF here, I could figure it out. The kernel of T, which is also the same as the null space of A, two different names for the same thing. I'm looking at the RREF here. I'm imagining zeros, an augmented matrix is zeros on the right. X3 or Z, if you prefer, is the free variable, but I got to imagine adding these negative coefficients times Z to both sides of the equation. So I get positive numbers on the right-hand side. It's always tricky for people to remember this. So Z being the free variable, X is going to be 43/3 times Z. Y is going to be 13/3 times Z. And Z is just itself. Z is the free variable. As Z varies over the real numbers, I could factor out the Z if I like and write it this way. And actually, I could avoid fractions here. I could multiply this vector by any non-zero constant, like 3 might be a good choice. And if I did that, I get 43, 13, and 3. It still works because Z is arbitrary. I can multiply this vector by any non-zero constant. This is an algebraic confirmation that the kernel of this transformation is aligned to the origin, right? If Z is 0, this is going to be the 0 vector. This does go to the origin. It's a one-dimensional subspace of three-dimensional space. Subspace in these geometric examples means typically lines to the origin or planes to the origin or some higher dimensional version of that. I also, with the spanning idea, could write this as the span of this one vector. What should I call this vector? I don't know. How about W? Span of W. Because what is a span? Back up here, I said these three vectors spans R2. What that meant, you may have forgotten already, is that any vector in the plane can be written as a linear combination of these three vectors. R2 equals the span of them, the set of all linear combinations of them. The kernel here is the span of this one vector W because that's an arbitrary linear combination of one vector, all scalar multiples of it. When I write this, I don't mean W is the only vector in the kernel. Never, ever, ever think that from now on, because I've just told you not to do it. I mean all scalar multiples of W forms the kernel. The kernel here is an infinite set, even though I only have one vector in it. W being one non-zero vector does form something called a basis for the kernel. This one vector is a so-called basis for the kernel of T. What does that mean? It's a new word. For one thing, it means it spans the kernel. For another thing, it means it's a linearly independent set. It's a linearly independent spanning set of the kernel. What does that mean? Linear independence for one vector, any non-zero vector just by itself will automatically be a linearly independent set. So that's easy. I just said any non-zero vector as one non-zero vector set by itself is a linearly independent set by definition. But what does it mean in general for a set of vectors to be linearly independent or not? In general, if you've got n vectors, v1, v2 through vn, is a linearly independent set if what happens? If when you have an arbitrary linear combination of them happening to equal the zero vector, the only way that can happen is if all those coefficients are zero. The only solution to that equation for the C's is trivial. That's what linear independence means. This definition, hang with me here, we're almost done. This definition applies to arbitrary vector spaces. Not just vectors you're used to, but vector spaces in the abstract, and also other particular vector spaces that you're not so used to, like function spaces. These V's could be functions. And that's going to come up on the homework. Again, when you have one vector, linear independence is easy. If that one vector is not the zero vector, so in Rn, it's not the origin. With function spaces, it's not the zero function whose graph is the horizontal line on the horizontal axis. If you got one vector that's not the zero vector, then that set is automatically linearly independent, because the only way a scalar multiple like of W here could be zero is if the scalar is zero. If you got two vectors that are both non-zero, they will be linearly independent if they're not scalar multiples of each other. With ordinary vectors that are arrows, that means they're not parallel. And they're going to be linearly dependent if they are parallel. A set that's not linearly independent is called linearly dependent. If you got three or more vectors, then linear independence gets harder. But let's end by relating this back to the three vectors here, v1, v2, and v3. Does this set of three vectors form a linearly independent set? The answer is no. They form a linearly dependent set. Why? We already proved it, because the kernel is non-trivial. That's why. If I have a linear combination of these three vectors equaling the zero vector, that's equivalent to a times x or t of x equaling the zero vector. In other words, solving for the C's down here in this definition is equivalent to solving for x when this equals the zero vector. And we found non-zero solutions. So this set is not linearly independent, it's linearly dependent. And therefore, these three vectors, even though they span R2, they span the plane, they do not form a basis, because they would have to be linearly independent as well. And they're not, they're linearly dependent. Could I get rid of one of these vectors and get a basis? Yes, you can. In fact, you could get rid of any one of these vectors, say the third one, and the remaining two would be a basis for the plane. Would form a linearly independent spanning set still. It'd be two non-zero vectors that are not parallel in the plane. It's going to form a basis. The standard algorithm for coming up with a basis for the image, same as the column space of the matrix, is to do your RREF as we did in Mathematica, and notice where the pivot positions are, and use the original matrix's columns that are pivot columns as your basis. So the first two columns here, this REF, have pivots. They are pivot columns. Therefore, the original matrix, use the first two columns, is the standard algorithm for coming up with a basis. Question?
So if we have linearly independent set of vectors, what would the REF look like? Would it just be diagonal, just the identity matrix?
If it was a square matrix and your columns were linearly independent, if you go to REF, it would be the identity matrix. You're right.
Yeah, well, if you have the case of, well, in this case, you have three vectors and a two-dimensional codomain.
Let's do an example where it's a tall and skinny matrix. Quick to end here. Okay, those two column vectors are linearly independent, but this is a 2x3 matrix. What does the REF look like? Or 3x2 matrix? It looks like the identity matrix in the top part, but there's a row of zeros. The corresponding transformation would not be onto, but it would be 1-to-1. The kernel would be trivial.